Linear trends take us back to chapter 13. Chapter 13 introduced us to regressions. And we learned that a regression equation looked very similar to this equation. Now, who can tell us what the difference is between this equation and the regression equation? There is a bit of a difference.
Is it not the T, the time?
Okay, what is it?
Well, is the time that happens within like this year to next year, while the other one just had an X value?
Exactly. That's the exact answer in terms of what the difference is between your standard regression equation from chapter 13 and this particular one. In chapter 13, we had y hat equals a plus bx. And of course, x was our independent variable, whatever it happened to be. In linear trends for indexing, or for a time series, for linear trends for time series, we're looking at x being replaced by t. Okay. The logic of the regression is exactly the same. It's just that now we're saying that t, right, is any value of time that is selected. So we're very focused on time because we are in the time series chapter, which is in the time series analysis. Of course, y hat is still the projected value of the y variable. A is still the y-intercept. B, or beta, still the slope of the line, which measures the change in y over the change in x, or t. Sorry, the change in y over the change in t. So as the years go up by 1, right, what happens to the projected value of the y variable, whatever the y value happens to be? So the linear trend plots. We have a time period 1 through 9. We have corresponding years, 2005 to 2013. We have something going on that we're measuring, sales. And then we have a trend line, okay? So the sales line is green. If you were to plot these numbers and then a scatter plot and then connect the dots, you would get a green line that looks like this. However, if you were to create the actual regression, the linear trend equation, you would see an output that looks perfectly straight, because that's what the regression equation is, a linear line. You would see a perfectly straight line. And so year 1 would actually be 3, year 2 would be 5, etc. Okay? So we're going to put that to practice in a moment. So in doing this, we're going to use the methods we learned, right, in chapter 13 to find the best relationship between two variables. And we're going to code each year 1, 2, 3, 4, 5 as opposed to 1993, 94, 96. Okay? All right, sales of Jensen Foods, small grocery chain, Southwest Texas. Here are the years, 2009 and 2013. If we code the years as the time, we would say the first year, 2009, is coded as 1. This is the first year. 2010, number 2, etc. When we do that, we can then use the regression equation to construct the predictive tool. And so here we go. If we were to go into Excel and run a simple regression and put the Y range as C1 to C6, right, it would say that sales, look, C1 to C6 is the sales data, okay? Sales depend on the independent variable, also known as time 1 through 5. So time 1 through 5. Okay, so instead of using the year, we would use the time. Okay, and we would, of course, check label and hit OK. And out would pop a regression equation, or I should say a regression output, and we would see a y-intercept of 6.1. Okay, and we would see a beta of 1.3, a beta of 1.3. Now, that's a straight line, so that would represent the orange line here, which means we were able to transform this green line into an orange line, which is a straight line, which is the goal. Again, predictability. But who can interpret this 1.3 and who can interpret this 6.1? Let's start with the 6.1. Who can interpret that?
Well, I know that's the A or the intercept,
Y-intercept, okay.
and the 1.3 is the slope, which would be multiplied by the time.
Well, let's focus on the 6.1. How do we interpret that 6.1? So that's good. If we take this orange line and we continue the trend, it'll cross right here at 6.1. Now, what does that mean? If I hold the X variable to 0, there are still sales being had. Okay, that's what the y-intercept always means, right? If I take X and make it 0 in the equation, meaning I turn this 1.3 into 0, and 0 times t is 0, there's still some y happening, right? Because y would then be 6.1, because these would all be 0. That's useful to a degree, but really it's all about this beta, right? In regression analysis, big fans of the beta. We learn how to test betas, we learn how to reject insignificant betas, etc. So how do we interpret that 1.3? Don't overthink it. It's a slope. Changing y over changing x.
It means that for every year, sales go up they go up by 1.3.
Exactly. Changing y over changing x, right? And of course, as I always told you, x is what leads y. X determines y. So we start at the bottom. As x goes up by 1, in this case by 1 year, sales go up by $1.3 million. Okay, as years go up by 1, sales go up by whatever the beta is, 1.3. Now, let me ask you a different kind of question. If we did not code, right? If we did not code, meaning we didn't even have this beta, this B right here. We just had years. Let's say we use years as our y variable as opposed to this, okay? Or as our x variable. What would be different about this 1.3? What might be different about it? What might it look like? Again, the question is, right now, your x variable, right, your independent variable is years, 1, 2, 3, 4, and 5, the coded number here. Why didn't we use these years? What would it look like if we had used these years?
The number would be a lot bigger.
Right. And then what would be the problem there in terms of the interpretation? Instead of 1.3, it'd be something a lot bigger. Perhaps it'd be in the thousands. What then would be the issue?
It would be harder to make that estimate. It's because you're really multiplying that sales times the time, and that number would not reflect the exact figure that you would need.
Right. If this number were in the thousands, let's call it, I don't know, 3,000. Then the interpretation would be very different. You'd be saying that as years went up by 1, sales go up by 3,000. And of course, the interpretation here is in million. So if this is 3,000 and we start adding zeros, then we're talking, in the billions, right? Because we would say 3,000 million. So you have a very strange interpretation of this data, a less useful, more illogical interpretation if you don't code. So the reason why we code is to say, okay, as this goes up by 1, then sales go up by something reasonable like 1.3, which is 1.3 million, very easy to believe because the sales are, in that area, as opposed to something very extreme like in the billions. So keep in mind the logic behind coding is to improve the interpretation of the regression equation. Okay, so it's not just a random thing to do. Let's code for the sake of coding. No, we're coding because it improves the logic of the regression equation. Our ability to interpret the data becomes much more logical. Okay, and it's quite easy to code. You're just doing one through whatever number. Okay. Next, we close it out with nonlinear. So a linear trend is used when the data are increasing by equal amounts. Okay, so we have data which tend to be increasing by equal amounts here, meaning we don't have anything, any strange looking curves. They tend to go up and down by relatively equal amounts, 7 to 10 to 9 to 11 to 13. So they're changing by relatively equal amounts, giving us a curve that looks, it's not linear, but it's also not, going in a U pattern. It's not going in a strange shape. It's kind of just rising up and down in time. Okay, when the data are increasing or decreasing by increasing amounts, right? So it's not just going up and down by, relatively the same numbers. It's going up and down by increasing or decreasing numbers. Okay, so that's an issue. That's an issue. Here is an example of that. So this is increasing by increasing amounts. So we see the numbers are holding steady, but then there's an explosion here, right? It starts to increase by significantly increasing amounts. And so you have a line that looks a little bit more tougher to deal with than the other line. So this is called a nonlinear trend. By definition, a trend which has data that are increasing or decreasing by increasing amounts. When data increase or decrease by equal percent proportions, a scatter plot will show a nonlinear pattern. Okay, and the increasing percents, okay, is what we're talking about, which creates a line that may look like this. So we have to do something different. We can't just, utilize our standard equation after we code the years. We have to implement something different, and that's called the log trend equation. Very simple to do in Excel. We must transform the data to create a linear relationship. We will convert the data using logs. When you take logs, you are what's called linearizing or creating linear data that is currently not or non-linear. So the bottom line, how do you change data which is non-linear into linear data? You take the log. And if you go back to your college algebra classes, you'll recall, right, the whole logarithmic process with your standard base of 10. That's what we use here. But of course, you can change the base depending on what you're trying to do. But in this case, we are taking a base of 10. Okay? So there's a couple of things to know. Let's grab the data first of all. Let me see here. Nonlinear trend. Okay, so this is our data, right? And all I've done is put up the same data that you have in your slide. And let's see what's taking place here. What's happening is we are going to transform this green line into this line, okay, making it a straight line. How are we going to do that? We're going to run a regression after we convert the data into logs. Okay, so look at this data right here. We have code 1 through 15. Very simple to do if we're in Excel, right? I have my years. I'm going to create a column, and I'm going to call it code. So I have code right here, right? And I'm going to put for 1999, number 1. 1992 or 2000, number 2. Okay. Now, in Excel, it's very simple to create the next set of data. You just grab both of them and drag. Grab them both and drag. Okay, I'm going to change my alignment right here. There we go. All right, so that's my code. And then I want to create logs, which means I'm creating a linear set of data from an earlier set of data. So log sales, very simple to do, equals log right? You could do log 10 if you choose to, but log will give you the same thing by default. Open parentheses and enter my data and hit return or enter, okay?
So Dr. Manier, you can do log 10 to get the answer.
Yes, you can, but
Okay.
you don't have to because the log is the same default.
Okay.
Log 10, so you don't necessarily have to. So just log, grab my data, hit enter, and I am done. And actually, I think it actually asked me for, yeah, it asked me for base, but because the default is 10, I don't even have to enter that. So there you go, and then I can drag, and I am done. I have created log sales data. I've created log sales data is what I've just done. And then I just run the regression, okay? So kind of your standard regression. What is my inputs? Y range.
Would not your log sales be a Y?
That is correct. Log sales will depend on the year. So we're going to grab log sales right there. And then for the X range, we're interested in the code. All right, labels are checked. Let me create a new output range here. Let's drop it right there. And we hit OK. All right, so here's my output. Okay, and you'll notice it's the same. Move it over here. The same output. They're very interested in these almost always. So here is the 205 as my y-intercept, and here's my 0.15 as my beta. Okay? Any questions there? Okay. We have a giant R squared. That's because there is a very strong correlation between years and sales, right? You know, sales does strongly depend on the years going by. So they are almost perfectly correlated. And we have 15 observations and other stuff that we're very familiar with, and we should be at least, in terms of this output. Okay.
Excuse me. Do we need to do a like a scatter plot and a linear to kind of compare, or we just need to do the regression analysis once we did log?
Right, good question. In some cases in Connect, it'll ask you to do a scatter just to compare, right? And if you were to do a scatter, the initial scatter at least, you would be taking this data.
Okay.
Okay, and you can run the scatter, and it will come out, you know, just like in the slide, a nonlinear, or it's also called a curvilinear, nonlinear set of a graph.
Okay.
But then when you ran it based on this data, right, and this data, okay, your output will look much more, look identical to this.
Okay.
Okay, good question though, because you should always run a scatter plot to see what your data looks like. Just in general, like in life, if you're asked to analyze data, the scatter plot is the easiest and really useful piece of information to see what it is you're working with, to see where you want to go next. Okay, so there's our output. Okay, and then before we get to this, which is actually the last slide, let's do some interpretation. The first issue here is that the beta is a log beta, right? It's a log beta. And the thing is, once you log something, you no longer have the ability to use it outright as an interpretive tool. We really can't say right now that, you know, as years go up by 1, sales go up by 0.15. That's not something you could actually say, because 0.15 actually comes from a logged set of data, and once you log it, you can't necessarily state it like that. You can, however, because logs represent linear rising data, things have changed on a percent level. If you look in your book, yes, page 654, here's the language. It's very good language. The equation is the log form. What do I mean? I mean that if I were to write this equation, I would write y hat equals 2.05 plus 0.15, let's round it 2 decimals, so plus 0.15t, right? Which is right here. We see your basic equation from chapter 13. Listen to the language, page 654. This equation is the log form. We now have a trend equation in terms of percent. And I can't underscore that enough, but percent of change. That is, the value of 0.15 is the percent of change in y, again, is the percent of change in y hats for each unit increase in t. Let me read that again, because that's really the big takeaway. The value, 0.15, is the percent of change in y for each unit increase in t. So, what is t? Well, t is time. So as time goes up, as each unit of increase happens, meaning as time goes up, or as years increase by 1, 0.153 is how much sales increase in terms of a percentage. So that is a very big takeaway and a very big difference from what we've done before. What would this be from before? Well, in chapter 13 and 14, we would have said, as years go up by 1, right, sales go up by 0.15. And if this were in thousands, we would say $153, right? We'd move it over 3 decimals like we did in the last practice, or last participation, right? So we would move it decimal over and we'd be done. It'd be just a regular change. Now, however, with logs, we are saying that as the years go up by 1, sales increase by 0.15%, okay, which is a big old difference from 0.15. Okay, any questions there?
No questions.
Okay, so when we take logs, let me just close this out with emphasis. If we take logs, we are now talking about a percent change of our y variable, as opposed to a unit change. Okay? All right. Now, one other issue is going to exist, and you'll see this a lot in your homework, and you'll see it on the exam, and you'll see it in life if you go down this quant road. Estimate the sales for the year 2017 using the transformed linear trend equation. Very interesting. As you know, a regression equation's best value comes from the fact you can use it to predict the future. On this current set of data in the years, do you see 2017?
No.
You do not. You do not see year 2017. So we have to use our predictive tool of the regression equation. Now, if we had 2017, like let's say we went all the way, and I'll actually pull it up, right? Look, let me go to 2000, let me create 2017 right there. And the corresponding code would be, look at that, 19, right? The corresponding code would be 19. Everybody sees that, yes?
Yes.
Okay. Now, if the question is, estimate the sales for year 2017, also known as year 19, how do we do that? Well, the same way we've always done it in the beginning. Here is our regression equation, okay? Instead of t, we're going to throw 19 in there, because that is the year 2017 we're concerned with. We're going to use 19 for all the reasons we said before. We don't use the actual year because it messes up the beta, which messes up the ability to predict with the equation. So we're going to use 19 right there. When we solve this problem, typically we would say, you know, whatever y hat now is, that's our answer, right? If we're trying to estimate sales for the future, 2017, typically, chapter 13, 14, we would be done. We would say sales are 4.97. The problem with saying the sales are 4.97 is that 4.97 is a logged number, okay? It's a log number. So how do we transform this log number into actual units of sales, actual dollars? How do we go from logs back to your standard numbers? That's the question. And there's a very simple formula and a very simple answer for that. It's called taking the anti-log, okay? Taking the anti-log. So if we have a log number that we want to transform back to your standard number, meaning we want to take the opposite or the anti-log, here's our process. Find the anti-log of y hats. What we do is we have some y hats. We use 10 to the y hats in Excel to transform whatever y hat we have back to a standard number. Okay? So let's see what that looks like. Now, if we go equals 10 carat, okay, or hat, raised to the, those are 3 ways to say that, 4.96758 equals, there is our number, right? 92,809. 92,809. So that 92,809 is actually $92,809 are the sales for 2017. If you put an answer that your sales are 4.96, you might even say million, right? You would be wrong. That 4.96 is a log number. It's the log of what? What is that a log of? It's a log of 92,809, right? If I were to take equals log and grab this number, guess what? 4.96, etc., 4.97. Okay? So very simple to take a log number, 4.967, and transform it to its anti-log. What is the actual dollars? Because these aren't dollars. These are log dollars. You got to get this back to regular dollars. Okay? And the way to do that is take the anti-log.
Okay.
So let's run another example here. If I were interested in, actually that's the wrong one. If I were interested in, okay, if I were interested in year or 2022, right? Just randomly chose number 2022, right? Stretch this out to 2022. There we go. That's 2022. That corresponds to a T of 24, right? I would take that 24. Let's actually do the math. So 2.0, I just want to use 2 decimals. 2.05 plus 0.15 times, and instead of 19, I would use 24, right?
Right.
Okay. And so, my answer, one could say, is, y hat equals 5.65, right? And that technically is what y hat equals, okay? But the problem with that is that's not dollars. That's log dollars.
Correct.
Okay? That's log sales. So I would take equals 10 raised to that number, enter, and then I actually know what my my number is, okay? And my number in this case, of course, would then be 446,683. Okay, so that represents the sales number for year 24, okay, or year 2022.
Okay.
Okay. So not so hard, but it is an extra step that is introduced. Another thing, let me actually say this. Another thing that Connect will ask you about is percent changes. Percent changes. So you can read about that on page 654, where the log number, like the log V here, is 0.15. And in some cases, you'll need to take the anti-log of that to understand the true percent change. Okay? You can read about that. It's pretty straightforward on page 654.